All right, we are being recorded, everybody. So let's jump right into it. So here were these questions that we had. All right, so let's talk about the different types of transducers that we have. So a couple of the types of ultrasound so in the last lecture on Friday, we talked about how a transducer works, what the piezoelectric crystal is actually doing. Now let's actually talk about how the transducer itself is constructed, and we'll talk about these different types of transducer, plate, linear, phased array, annular, things like that. So back in the day, the dynamic ultrasound imaging could be done with mechanical motion, where the transducer head can actually wobble, which is what's shown on the left. It actually can be done with a rotating element, as shown on the right. So the actual transducer elements are rotating inside a cylindrical geometry and sweeping out that fan blade around. The thing about these guys are, each one of these is you have one piezo element here and here. Now this one has 4 together. But because one transducer element can only shoot out one beam, then if you only have one transducer element, you have to somehow move that element to shoot in these different rays to create this fan beam geometry, it's called, right? To get a bunch of parallel A-line scans to generate that B mode image. That, as far as I know, is not used medically anymore. I've never seen one that has a single element in it. So we have a much better way, a much faster way of doing it. So, and one of the better ways to do it is to use what's called a linear array. All right, so a linear array is a whole bunch of different transducer elements parallel to each other. So what I'm showing here, if you look at this picture in my crude PowerPoint drawing skills, each one of those small boxes is supposed to be a transducer element. All right, and you can control exactly when they fire and then when they're listening. So in a linear array, you have any number of transducer elements. Maybe it's times 128, something like that. It'll be a lot, more than 2. So the picture's kind of accurate. It's not 2, it's not 4. It's maybe 100, 200, something like that. And you control when they fire. And in that way, you can just fire this one first, and then this one second, and this one third. And so the beam will be swept along the array. You fire and listen, and then move over and fire and listen, and move over and fire and listen. And you can either fire one element at a time or a subset together. So actually what I'm showing, for example, on this example that I just made up, say that this is elements 1 through 10, you can control all of those to fire together, because the one transducer piezo crystal is pretty small. You put 10 of them together, it's a decent sized beam. And all the 10 of those can fire together. And then you listen on those elements. And then you shift over and fire another one. It looks kind of like this. Those fire, and then you listen. Echo, echo, echo. All the echoes done. Fire again. Listen on those. 10 through 20, 11 through 20. Listen, listen, listen. Move over, fire, that would be like 21 through 30. Listen, listen, listen. 31 through 40. Listen, listen, listen. So in this way, you get a bunch of beams sweeping out. You're going to image everything in here in the patient, and nothing physically has to move, right? So it's all electronically controlled. I don't know of anything where something's really physically moving anymore. It's just way faster to have the electronics do it. So you could do all 128, or you can gang them together and do 10 at a time. You can do 4 at a time and narrow your beam. You know, it's completely programmable. So you can set the beam width to be exactly what you want it to be. But the key is that a subset of elements fire at one time. So this is a high-resolution micrograph of a linear array. So you can see all these interconnects coming in. The arrays are here. So a very, very small 192 element linear array. So you can't even hardly see them, but there's basically 192 lines going through like that. You can kind of see the lines in that picture. This is an example of a linear array up here. Each of these guys, these things that are sticking up, are the piezo crystals. All right, so you call that the array element. There is a pitch to those guys, right, where the pitch is the distance between two centers. So it kind of tells you how big the thing is and how many you have. So distance between centers. And then they're characterized by something called the kerf, which is the space between elements. How big is that? And then you can just calculate how many elements you'll fit in there. So that's an example of a linear array. And again, you could fire each one of those individually, or fire 1 and 2, and then 3 and 4, 5 and 6, or 4 at a time, whatever, all programmable. You can make it more complicated and have a two-dimensional array, right? So if you understand what's going on in A, the linear array, well, then just make it a two-dimensional array. When you could do exactly the same thing. Of course, it's going to take way longer to take your image now because you have to fire subsets of all those at a time, but there you go. And then there's this idea of C, the annular array, right? Because this is a annular. Because a circle like that, that's an annulus, right? So this is still kind of, this is not a linear array because there's nothing line-like about this, but it's a series of concentric circles, or annuli, that forms this annular array. And then you can fire different subsets of these to focus the ultrasound pulse down or not. They can fire sequentially in or out. So those are just different types of arrays. The idea of a linear array, though, is really what I'm going to be showing here on the screen. All right, so a linear array, whether it is rectangular and flat or curvilinear, meaning you get this trapezoidal field of view, they are operating on exactly the same way, right? So this is just the geometry, whether you want a rectangular field for some application, maybe a kidney, trapezoidal field if you're doing obstetric imaging, that's just a design constraint. The idea of a linear array is the same. They produce an image by activating a subgroup of the transducer elements. So in the animation I was showing here, it looked like I was firing, what, about 4 of them at a time? A subset of those guys will fire. That forms one A line. Then you shift the active elements over to acquire the next line of data. But you're firing and listening on a subset. And then you can walk the beam all the way across. Does anyone have any questions on that at all? Here they are firing again. Fire 1, listen. Fire 2, listen. Fire 3, listen. Fire 4, listen. Fire 5, listen. And of course, this goes very, very, very fast. We did that calculation last time. So this is, the pulse repetition rate is about 2 kilohertz. So it's firing out about 2,000 of these pulses a second, which is pretty fast. Obviously, my animation is not that fast. Any question on that? Okay. So that was the linear array I just showed you. Now, here's where students get confused because there is the second type of array called the phased array, which I'm showing here. And it looks the same. You would be forgiven for thinking, oh, these two pictures look kind of the same. Yeah, they do, but they are not operating the same at all. And the key primary defining difference between them is that in the linear array, a subset of transducer elements activates. You fire and then listen. In the phased array, all the elements are activated on every single shot, right? So that's being described here in B. A phased array produces a beam from all the transducer elements firing with fractional time delays in order to steer and focus the beam. And we're going to see some examples of that. So by controlling the phased array, the word phase means you're controlling the phase of the firing or when each of those elements fires. And then you can steer the beam or focus the beam. And that's really the primary difference. If you saw all those elements, those two pictures, they look the same. Are you firing all of them on every shot or a subset on every shot? That'll make the difference between a linear array and a phased array. So this is what I'm showing. So with all of those, 128 elements or 90 elements or whatever it is, you can set the delay on those guys. And that's what they're trying to show up here. What they're showing on each one of these lines is like, when do you fire the pulse? So if the pulses are firing sequentially from left to right in sequence, then you can have a beam that's actually shooting off in this direction. And that's just because the wave fronts from each of those guys line up. Just by shifting the phase delay here, you can actually make the beam shoot out the other way. And if you control the phases a little bit intelligently, you can also just make it go straight out, but kind of get focused into the middle. So it's beam steering and beam focusing based on what order you fire all those elements in. It kind of looks like this. So here's an animation in the upper left, right? So in the upper left, if you follow each of those pulses coming out, we're starting at the bottom is firing first. So this is first, and up here is like last, right? Because the direction of a wave is just where the wave fronts add up. So I'm firing the bottom one first, so its circle, each element sends out like a spherical pulse, like dropping a stone in the pond. You just delay, so phi is the phase. So the second one right above it is just phase to fire a little bit later, and then one above that a little bit later, a little bit later. By the time they all add up, you then have a beam which does not go straight out, even though the front of your transducer is flat, you're actually shooting off a beam at some angle theta, completely controllable by just the phase, because the wave that goes out is the wave addition, it's the wavefront addition of all the elements. All right, and if you guys want to see this, I have just a small animation on that. It's just a YouTube video. There is no sound with this, but this is just a link to this video. So these are some people who make software on this. So just watch what's going on. So just watch that there are sliders. So that's the point of a phased array. You can dephase each of the sensors. So it's just like a little mixer board. So she's setting up the sensors where she wants the one on the left to fire first, the one on the right fires late. Do you see how all the wavefronts add up to make the beam go off this way? Oops, whoop, whoop. I can't draw on that, sorry. The beam goes off that way. Make that big, there we go. Automatic mode. Steering angle completely set. So the steering angle, what angle you want to set it out at, it's just let by those fires. So this is cool. She set that on automatic mode. You set the angle, it figures out where to go. Now it's sending a wave way to the right, right? It's steered at like 59 degrees from normal, 25 degrees from normal. So a nice flat thing. Now she's actually going to focus the beam, and this is what's cool. So instead of just sweeping it from left to right, she's going to focus it by having the ones on the outer edges fire at the same time, and then it's going to work its way in, and watch what happens, right? You can actually make that beam focus at any place that you want. So it's not working its way from left to right. The ones on the outside fire first, and then they work their way in. So just by controlling that, phase, that's how you're able to recreate such an image and make something either go out, or you can make it focus in like that, or whatever. And that's a phased array. So you might think, wow, phased arrays are awesome. Everybody should use phased arrays. That's true. You can talk to someone in Dr. Mayev's group. The problem is they're just really expensive. You have to have very complicated electronics for every single channel. So it's not that you can't do it. It's just way more cumbersome and way more expensive. They are better, but harder to use electronically as well. So that's the idea of a phase array. You want it to steer or be focused somewhere. All right, so the whole goal is to send out these multiple A mode scans where you're kind of eventually coming up with some trapezoidal pizza pie shaped image through the person for the most part. And within that pizza pie image, you want to be able to resolve certain things. So all of your images are going to be characterized by 3 types of resolution, really. That being the axial resolution. So now we're just defining some terminology. So the axial resolution, obviously this is the axis of propagation. So the axial resolution is just here, right? As you're shooting something through the beam, what's the thinnest thing you can measure that the beam has to travel through? There is the lateral resolution. Right, the lateral resolution. So then the lateral resolution is limited by the width of your beam anyone. Remember, each of those pizza pie wedges is composed of multiple beams that goes through. So the width of that beam is going to be given by the lateral resolution. And you can actually see right here that if that beam is focused, there is a point where the lateral resolution is best. So the lateral resolution right here, so let's call it like R sub L, is better than it is out here, R sub L prime, right? Because the beam is way thinner up here. So most transducers do focus their beam, and they are set to be operated at a depth where the beam is focused, and they'll have best resolution there. It doesn't mean that you can't image things out here. It just means that the resolution is not going to be as good out there. And that's just the way it goes, right? So most of them are, again, an obstetric one, like they know where the fetus is. They're not guessing, gee, I wonder if the fetus is like 80 centimeters away or 3 centimeters away. It's like they know exactly where it is. A lot of ultrasound gets done for cardiac applications. When they put the cardiac ultrasound transducer on you, they know exactly where your heart is, right? It's not a mystery. So they're using a transducer that focuses the beams at the depth that they want to image. Maybe they're trying to get good images of your heart valves or something like that. And then the third resolution is this elevational, which is the thickness of the slice, the thickness of the pizza pie wedge. And that's just given right here, right? How tall is this thing? So the resolutions in ultrasound, those 3 dimensions are actually different. The axial resolution is not the same as the lateral resolution, is not the same as the elevational resolution. All right. Typically, the elevational resolution is the worst because that whole thickness of the slice might be like a millimeter, and everything else is probably under a millimeter for that. But you know, you're only looking at one slice at a time, so you really don't care. How do we make these beams be shaped? A lot of them actually have an acoustic lens, a lens for ultrasound. It is built onto the front of the transducer, and then that makes the ultrasound pulse focus in this dimension, and you'll have optimal elevational resolution, say, right there. All right, so acoustic lens is just a piece of plastic that it's a Z impedance match to the ultrasound wave, but it'll deform and bend an ultrasound wave just like a glass lens bends light from the optics that you know. There's a couple ways that you can do focusing. So again, this is just kind of showing ways that can be focused. Ultrasound waves is just build a convex acoustic lens, and then you'll just, instead of having a beam that just kind of comes straight out, which is okay, but remember, best resolution where the beam is smallest, focus it through the lens, and that beam actually gets focused like that. And then you can use it at that depth, which would be the best axial resolution. Or that's the lateral resolution. Or if you want, you don't need the acoustic lens, you could just use where the transducer head itself, the element array, is bent like that. And then, no matter how you fire them, the wave is always going to be focused at some depth. So self-focusing due to the curvature of the elements themselves. So these are things that you can do. Or you can use the phased array, right? A phased array, if you control the phases, you can also focus it. So if you say, how are ultrasound waves focused? Use the phased array, use an acoustic lens, or just use a spherically focused element that's already bent. All right, so there's 3 different ways of focusing ultrasound pulses within the body that you've just now seen. Here was that third way I was talking about, so focusing with the phased array. So again, in a phased array, you have this set of array elements. It is programmable, and as you see, these guys are firing out here first. And so the wavefront from the outer elements gets ahead of the wavefront from the inner elements. And by the time they add up, the wavefronts then look like that. That's just wave dynamics. That's how waves add up. So, as it says, the whole point of phase differences of the ultrasound elements, it results in a minimum beam diameter, which is the focal distance, at a predictable depth. They know exactly where it is. And that's how a phased array would do it. For a linear array, again, just what I said, you can use an acoustic lens on front. And here is kind of your typical convex probe. And say this thing has an acoustic lens built on front, which is this part right here. It's the screen bit, right on the front. You know, they don't have to be, they're not super big, and it's completely monolithic. It's part of the transducer assembly. Okay, so that kind of sets the resolution of the instrument. So now what happens when you launch the ultrasound pulse into the tissue? So this was our transducer up here. And now I want to talk about what the different interactions in the tissue are. So here comes your pulse. You launch it into the tissue, and a couple things could happen. Some of the beam is going to get reflected. That's what we want, because that causes our echo. Of course, you want some of it to be reflected. Some of it is going to be transmitted, because there is transmission. This is, again, as we said before, this is good, because we actually want the ultrasound pulse to go deeper through the tissues and reflect off multiple structures. So we want some reflection and we want some transmission. There are other things that can happen, which is some of that ultrasound energy will just scatter away. So kind of non-strong echo. It's just kind of literally the energy gets scattered off of the microstructures in the tissue, and the ultrasound goes in every different direction. What I mean by reflection is that the pulse comes out and reflects back at you. But scatter is that pulse maybe doesn't come back at you, doesn't go straight, it scatters in all directions. So you might get some little echoes, but a lot of that energy just goes everywhere. It's kind of lost. And then some of the energy is just absorbed, which is not scattered. It's just the energy gets weaker as it propagates through the tissue. Remember, an ultrasound wave is a pressure wave. The pressure wave is trying to get all the molecules of the tissue vibrating together, and that loses energy as it propagates. It's not 100% efficient transmission of energy. So there will be attenuation of the energy as the pulse gets deeper. We call that absorption. So let's talk about that attenuation. So attenuation is this word. When a beam gets attenuated, attenuation is like the process of getting weaker. So the beam gets attenuated, the process of getting weaker. The beam at the entrance to the tissue was, say it was intensity I naught, some number of watts per square meter. Down at some depth, let's call that D, the intensity will be weaker. The intensity is going to be less than I naught. Why did the intensity drop from I naught? Well, there's three different mechanisms that could have related to it. One is there is just some absorption. So even if the beam reflected from nothing, it's just going to get weaker as it propagates through the tissue. The conversion of acoustic energy just into heat. All right, like I said, it's not a 100% efficient process of transferring energy. So that acoustic energy just gets lost. It's irreversible because it goes into heat. And once energy goes into heat, you don't get it back. So that's always going to happen. Then there's scattering, which we talked about, right? So scattering. Elastic scattering, non-specular reflections. This just means that if there's like little, well, okay, there's always going to be microstructures in all tissues, right? Because we talked about this at the beginning. Is any tissue completely homogeneous? No. Even at a cellular level, there's like little clumps of cells. There's like lots of little boundaries and interfaces, right? So there is no one organ, even an organ of your body, like a big kidney, is just kidney cells, and a big liver is still liver cells, right? You know what I mean? It's not completely uniform like a sheet of plastic. So this just means that, you know, some of the waves are going to go off this way, that way. This is scatter. Scatters out of the beam. Some of it might go back, and you might detect that as well, sure. But some of it goes this way, and some of it goes this way. Oops. Right? So the energy is conserved there, because it's not converted to heat and lost, but it's removed. Because if it's scattered out orthogonally, that's not doing anything for you anymore. It's not getting down to the depth that you wanted. Generally, this is going to be due to interaction with structures smaller than the wavelength. right? So if we're dealing with like millimeter-sized waves here, again, things that are 10 microns, you're not going to get a good echo off that, but they can scatter the beam intensity, and then it's just lost. And then, of course, the third thing that can make it weaker is reflection, and that's what we want, right? Because we want to pick up echoes. So here's your organ down here. You're trying to get some, and so some of that intensity is going to come back, which means, but that means that the intensity that gets transmitted through is less. Generally, reflections reflecting off structures larger than the wavelength. We call that specular. So specular reflection means it actually acts like a ray. It kind of goes in and bounces back. Non-specular means it just kind of scatters off everything. Specular reflections in optics are like when you look at a mirror and it all looks like a beautiful little image. Non-specular reflections are just when you see something like shiny on the sidewalk, but it doesn't reflect like a mirror. That's all. Like concrete can be bright to look at, but that's not a specular reflection. It's kind of scattering all the sunlight that hits a slab of concrete because it's very rough. So specular and non-specular. Those are just common words in physics. How does the absorption of ultrasound go in human tissue? Well, you guys answered this on the question. It roughly scales as 1/f, which means that things that have a lower frequency, so here I'm showing data from 3.5 megahertz and 7.5 megahertz, things that are lower frequency will penetrate further. So this is a phantom that they're shooting over here. So it's an ultrasound phantom. It has a bunch of dots in it that you can see. And where you're getting echoes from shows kind of how deep that 3.5 megahertz is going. Now you can barely see it, but you're kind of getting echoes from down here a little bit. When you go to 7.5 megahertz, that's a much higher frequency. Note, it goes not nearly as deep into the tissue, right? So 7.5 megahertz, higher frequency, beam does not penetrate nearly as far. And if you know that it goes as 1/f, then you could estimate 7.5 is basically twice 3.5, so it probably goes about half as deep, roughly. Okay, but the thing is, the higher frequency, you say, well, God, why would I ever use high frequencies then? It doesn't go very deep. The higher frequency can resolve the smaller features. So it is a trade-off. So what we're showing here is on these arrows, the 3.5 megahertz can basically resolve, these are small little occlusions in the phantom that are getting smaller as you go from left to right. And by my eye, you can see about 4 of those rows. But on the 7.5 megahertz one, you can definitely see 5 rows. Because you can see this guy, and you can see that 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 guy. So you can resolve smaller things, but just not as deep. And as I said, that's the trade-off with ultrasound. When you go to higher frequencies, you can resolve smaller objects, but the beam does not penetrate nearly as far because the absorption goes as 1/f. So this is just an example of, these are real clinical images of two of the nerves. This is sciatic nerve, all right? And they're taking images with 8 megahertz, 10 megahertz, and 12 megahertz. So you can definitely see the 12 megahertz, you're like getting nothing down here, right? You're not getting any echoes. This is the ultrasound probe is up, this is the top. So the ultrasound probe is at the top of that image. In the 8 megahertz image, you're getting pretty good echoes all the way from down here. I don't know how deep that is. I can't tell, but it's pretty deep. In the 12 megahertz image, you're not seeing anything. On the other hand, the feature that you're resolving at 12 megahertz is much sharper in that image than it is in that image. So you're getting deeper, but you don't have as good resolution. So the ultrasound user has to pick the right transducer. Here's another example. This is where they put in a test object, 0.5 millimeter object. And what does that look like upon reflection from 8 megahertz, 10 megahertz, and 12 megahertz? Well, you can see you are getting echoes from the 8 megahertz, but it would look like the object is almost that big. Whereas with the 12 megahertz, your resolution is much better, and you know you're actually imaging a small little object. So that is the degradation of resolution as you go to lower frequencies. So it's a trade-off, right? How deep do you want to image, and what's the size of the object you want to image? There's just no two ways around it. So in general, ultrasound imaging kind of follows this idea. Low megahertz, which I would call anything from 1 to 10, roughly has resolution from 1 to 0.1 millimeters. And that would be something like, I'm showing up here. 10 to 20 megahertz is getting to be pretty higher frequency ultrasound. And you can see here they're using that to image like a thyroid gland, which is pretty small, and they actually want to see some structures in that. I don't know what exactly that is. A normal thyroid gland in a, I'm sorry, that's a small little fetus in there. I apologize, because that's like a little human face. High resolution image of a very, very, very early fetus. The thyroid gland is down here when you're going to above 20 megahertz. And this is a really high resolution thing. They actually can do like 100 megahertz on your eyeball, where it doesn't have to penetrate very far at all. Those are the best ultrasound images I've ever seen. Most of the ultrasound you guys are ever going to encounter are probably going to be in this traditional 1 to 10 megahertz range, where most of the transducers are designed. Decibels, I want to introduce this idea of the dynamic range. So you guys are familiar with this decibel scale from optics, okay? They do it just a little bit different in acoustics. So if any of you guys go to work for Dr. Maev or Maev, and some of you probably will, the intensity of an acoustic wave goes as the pressure squared. So what they are trying to measure is the ratio of the pressure coming back from the echo over the pressure of the wave launched. And because the intensity goes as the pressure squared, the 10 becomes 20. That's where the squared went. So if you just take this equation and plop it in here, you have a ratio of p squared, but the way logarithms work, log of x squared, it becomes 20 times that log. All right, so the way the ultrasound people do is they will look at the echo pressure divided by the launch pressure, and the dBs of loss, there's a 20 out front, and that's where that 20 is coming from. It's because the intensity goes as the pressure squared. And that gives what's called the dynamic range of a system. So we're going to see this in a couple different medical physics systems. The dynamic range in all systems is kind of the range, it's the ratio of maximum to minimum. So how bright can something measure versus how dim? So we're going to talk about dynamic range with X-ray film, which is like how bright can something measure and how dim can something measure. There is no instrument that is perfect, that covers all ranges of things. There's just not. There's no instrument. And that's actually really hard to build, something that's sensitive at very low things and very big things. We're going to talk about this a lot, that the human body is amazing at. The human, for your hearing and for your vision, the dynamic range is huge because it's orders and orders of magnitude. From very dim your eye can respond to very bright your eye can respond. For hearing, from very soft your ear can respond to very loud your ear can respond, right? The limit of human hearing is something like 0 dB, and the loudest you can hear before it really starts to hurt is like 120 dB. So that's 12 orders of magnitude that you can hear. That's a lot. So for this is the way an ultrasound person would say, if they're using what's called a 100 dB system, it just means that the dynamic range, which is the ratio of the maximum pressure to the minimum pressure, is like 10 to the 5, right? Because 20 dB, I guess they don't put dB in there, but log of 10 to the 5 over 1, so this is just log of 10 to the 5, which is just 5, 100 dB. So if you go to work in an ultrasound lab, say, oh, I'm using a 100 dB system. What does that mean? That means whatever pulse you send out, you can detect echoes that get up to 10 to the 5 times weaker. After that, you will not detect it anymore. It's not infinitely sensitive, right? It can't be infinitely sensitive. Those echoes get weaker and weaker and weaker and weaker, and when do you stop detecting them? For a 100 dB system, you would detect it when it's 10 to the 5 times weaker. So that's the idea of the dynamic range. We will revisit that, but very important concept in physics and engineering. Lastly, I want to talk about artifacts, which are things that show up in the image that are not there. So here's 1, 2, 3, 4, 5 artifacts I want you to know. Speckle is, we talked about it before, so speckle are these non-specular reflections, interference from sub-wavelength granular structures in the tissue. And clinicians can actually use that to tell something about the tissue because it looks like static, but it's actually repeatable from them. It's not really static. There is acoustic shadowing and acoustic enhancement, which is regions of anomalous dark or anechoic regions, or enhancement regions of hyperechoic regions behind regions of either low or high attenuation. I'll show some pictures and explain that. You can overestimate the path by having these side lobes bouncing around. There is refraction, which is lateral displacement, which is an error in position due to the ultrasound wave actually hitting a curved interface and bouncing off to one side. And then there is what's called the speed of sound artifact. Something will be displaced longitudinally or axially because you calculated its location wrong because you miscalculated the speed of sound. Let's see some images of those. Here's speckle, right? So let that image clear up. Okay, so there you go. So here's two images on the left and the right. So this, all this stuff in this image right here that looks like graininess on your TV, that's not graininess. That is not noise. That is speckle. There is real microscopic structures in the tissue that are kind of scattering that acoustic sound out. And the clinician, they can differentiate the difference between the speckle from lungs and livers and kidneys. So they actually are used to kind of seeing what that looks like. It looks like noise, but it's not. It has to do with the structure, the subcellular, the kind of cellular structure of the tissue. Things that are much smaller than the interfaces will give rise to this speckle. It's an artifact. Here is acoustic enhancement and acoustic shadowing. What this means is that you see this large region here. The beam did not get attenuated in that region. That is a region of anomalously low attenuation. You are expecting things from deeper in the patient to be weak, but it went through this big, long, watery cyst where it didn't lose any intensity. And do you see how down here, it's actually much brighter than you think it should be? Look at what it should be over here and over here. Do you see how that's anomalously bright? That's called acoustic enhancement. It is due to that big lobe where it did not get attenuated. That is wrong. It is not super reflective right there. That is an artifact. It's not real. In the same way, this thing seems to have encountered, this beam seems to have encountered like two kind of rocky cysts or something. The beam was blocked, and so all the echoes underneath it are much, much weaker than they should be. You guys can kind of see these black bands coming through the patient. This is acoustic shadowing, right? There's not supposed to be this black band running through the patient. That is an artifact. It's not real. It's caused by the thing in front of it. The operator needs to understand that and interpret it. It doesn't mean there's a void in the patient. It means the beam has been attenuated more than you were expecting. Here's reverberations. So this is actually a GIF that I'm showing of reverberations, a lot of times always from an interface within the body, a lot of times caused by the diaphragm. So I think this is the ultrasound transducer is here. It is sending out pulses here. It's getting an echo from this thing, which is the diaphragm here, but it's such a strong reflector that you're measuring an echo at intensity 1, that pulse goes back down again, comes back up, and then you measure another echo. And then it's going to bounce down again and come back, and you'll measure another echo. And you can see a bunch of these, and they get weaker and weaker and weaker. But see all these lines here? This is not real structure. Those are what we call reverberations in the system. That is not real. That is an artifact. This image on the right. This is a guy who had a screwdriver stuck into him. I don't know what part. This is in its abdomen, right? This is an abdominal view of a screwdriver. This bright silver thing here is the screwdriver shaft, as the image shows. But look at all these lines underneath the screwdriver. Okay, those are reverberations. That's not real, right? That's just echoes that are being detected, and it's interpreted in the image as multiple things, but it is not multiple things. Those are reverberations. Anytime there's a strongly reflecting surface, you expect to see reverberations. And then the speed of sound displacement. right? So if you just encounter something, remember, what you measure is time always. Your measurement measures time, and you use that to calculate the distance. How do you calculate the distance? You need to know the speed of sound, the velocity, and you do a calculation. But what if your speed of sound is wrong? What if you are using the speed of sound of liver, but it actually went through a big chunk of fat, which has a different speed of sound? It means your calculation is wrong, which means that your calculation of distance is wrong. The speed of sound displacement, right? You're just actually plotting it at a different location because you measured the time, you calculated it, that makes it a distance, but it doesn't agree with the structures around it because it's actually in the wrong place. So the slower speed of sound in fat results in a displacement by about 6%. Things on the backside of things where you miscalculated the speed of sound will be in the wrong spot. That's an artifact, right? It does not mean that this patient has a huge gap in their anatomy. It's an artifact. You need to understand what's causing it and how you interpret that in your mind. You can't correct it. It's just this is the way it goes, but you understand what the image is. Okay, and let me just, one last thing, I know I'm running a little over time, but just mentioning the axial resolution because you guys were doing this before. We send out these ultrasound pulses going out. So an ultrasound pulse as a function of time maybe looks something like, oh, I don't know, it's like a little wave. All right, so the ultrasound pulse looks like this. All pulses have some pulse length, whatever that is. It's the time that it's on. You go blip, but when you go blip, how long is that pulse? That blip gives some spatial extent. We can call that L, the length. Typically, a few cycles. And I gave that to you. I gave you 4 in the Kahoot question. So typically, a few cycles, like 1 to 10 is typical for ultrasound. 1 to 10 cycles, that means that the length is, whoops. That means that if it's 1 to 10 cycles, that means the length is 1 to 10 wavelengths. Because a cycle is one of these. That's a cycle. 1 cycle is 1 wavelength. And of course, what Kane was trying to teach you all, and what you guys did in the multiple choice question is if this pulse comes in, interesting. If this pulse comes in and encounters 2 interfaces that are separated by some distance d, then that ultrasound pulse needs to go in, echo off the bottom, and come back. It goes down a distance d, it comes back a distance d. The total round trip distance is 2d. And that total round trip distance had better be greater than the pulse length, L, to avoid overlapping echoes, right? Because as soon as it hits the front, you get an echo. And when the echo off the back comes back, you want the echo off the front to already be gone. If the pulse L is bigger than 2D, it means the back is still reflecting off the front when the front is emerging and coming back. And then all you get is one big echo. You cannot detect a front and back surface. So 2D has to be bigger than L. That gives you this equation of D is greater than L over 2 that Kane gives you. But again, that's where that's coming from. Okay, that's enough for today. So that's what's going on with the beam inside the patient. I'll hang around and answer any questions on any of that stuff if you didn't get it. If not, have a great day. Get to your next class. Oh, I'm going to release the solutions for the homework set that you guys just handed in right away. So you can start looking at the solutions even before you get your graded homework back as you're preparing for the exam on Friday. Because I don't know when I'll get that graded. You might not even have it back and graded before the exam, but the solution manual is there. So if you had any questions about the laser homework, check out the solutions, okay? So have a great one, guys. I'll be here for a while if you want to chat about that. So I'm going to turn the recording off.